This lecture is going to be about computational learning theory. So let's look at two class input space. The input space contains data samples, and in this input space you have one region which is N, and the other region is P, which contains which have data that are in the negative and the positive category respectively. So these are some finite samples that we obtain from that sample space. These samples are then subject to some kind of a training. Machine learning model is used to train and to come up with a classifier that can classify those sample points into the pluses and the minuses. And this green dotted line is the classifier, and it does a good job in the classification, but there is one little training error, and which is natural. And so that training error, the expected value of that training error will be Rm, which is the empirical risk. Now let's put the original entire region back and look at the classifier. There is a region, actually there are two regions which the classifier will misclassify, and when we look at the entire region and the classifier superimposed, it can easily be seen that there are two regions which will not be classified correctly, and that reflects the true risk or true, or the that will be the true error. That's the dark blue and the red regions. Fact bound stands for probably, approximately correct bound. It's very detailed, and I will not get into the proofs. I'll just give you superficially what some of the results of this theory are. And so with a probability of at least 1 minus delta, where delta is a small number, we have this inequality. R true H is less than or equal to R empirical H plus square root of this whole expression. R true is the true risk, and so the true risk is always less than the empirical risk, R emp plus a big one term which is within the square root. And now let's look at it. So R true is the true risk, R emp is the empirical risk, N is the number of training samples. It appears both in the numerator here and the denominator here, but the effect is more in the denominator because you have a log in the numerator. And H is the hypothesis, which is a model. And the model is drawn from a hypothesis space, uppercase H. And VC here is the Vapnik-Chervonenkis or VC dimensionality of the hypothesis space. That gives you a rough measure of how complex the model is. And let's look at the role of the sample N. N is the number of samples. So what happens is, as the number of samples in number of training samples, as the number of training samples increase, the second term becomes lower, and so the true risk, this is upper bounded by empirical risk plus a smaller quantity. So it's a good thing if you have large number of samples. Then the true risk will be closer to the empirical risk. If you have small number of samples, then the denominator is low, and so this term becomes high, and so the empirical risk will be something, the true risk will be significantly more than the empirical risk. So our goal here is to keep the true risk as close to the empirical risk as possible. VC dimensionality this is where this term appears, the VC dimensionality of the hypothesis space, and it appears here. But again, this VCH, this factor predominates because the other one is within a log. And so when the VC dimensionality of H increases, then what happens is the true risk looks bigger and bigger than the empirical risk. And so our objective is to keep the VC dimensionality also as low as possible. I have not explained what the VC dimensionality is yet. And so this expression establishes a upper bound on the true risk in terms of the empirical risk and a second term, and this is can be identified as bias. We are neglecting noise here, so this term is the bias and this term is the variance. So it's the bias variance dilemma in another flavor. In order to understand VC dimensionality, let's get familiar with a concept called shattering. This is the formal definition of shattering, but I'll ignore this and go for a simpler definition. So this is the second definition, is a simpler definition. It's this one. A set of points S is shattered by hypothesis space H if and only if for every labeling of S into P and N, these are into positive and negatives, there exists some hypothesis H in the hypothesis space H that can correctly classify S. So we have a set of points S, and so we are looking at a hypothesis space. If there is some hypothesis lowercase h that can correctly classify all possible ways you can label the points in S, then we say that the points are shattered by the hypothesis space. And by labeling, what I mean is all possible permutations of pluses and minuses. If you have 4 points, there are 2 to the 4 possible ways you can label the points into pluses and minuses. And all 2 to the 4 cases must be able to be divided correctly by the hypothesis. An example will make it clear. So here's a set of 2 points in one dimension. And we have this blue bar here. Can this bar shatter S? S is the set of 2 points. Let's look at all possible dichotomies or all possible labelings of those 2 points. The red and the blue are the 2 classes. Maybe you can think of the red as belonging to the negative class and the blue as belonging to the positive class. And so if you place the bar between them, then it is able to do the correct classification. It separates out the red from the blue. And it does so here too. For this labeling of the points, when both points are blue, again, the bar is able to correctly classify. In this case, it has to be placed on one side because you don't need to separate out the two blues. There are no reds. Likewise, it can classify this labeling of the points into two reds too. In other words, this bar can shatter a set of 2 points in one dimension. Yes, it can shatter. Can the bar shatter 3 points? Let's see. There's no way you can place the bar anywhere which will separate out the 2 red points which are at the extremes from the blue point. So this bar cannot shatter 3 points. No. Now let's go over to the definition of VC dimensionality. The VC dimensionality of a hypothesis space is the maximum number of points that can be shattered by some hypothesis in H. So again, some examples will make it clear. Let's look at the VC dimensionality of a circle in 2 dimensions. So the hypothesis space H is a set of unit circles and of any center. So we are free to move around the circle any way we like, but the size of the circle remains fixed. It's a unit circle. And can 3 points be shattered? Let's see. Now, here in these 3 labelings, we are labeling 1 point as red and 2 blues, and we need to enclose the red point, and we are able to do that using the circle in all 3 cases. The red point is getting enclosed. In this set of labelings where there are 2 reds and a single blue, again we are able to enclose the reds. So in all these cases so far, we are able to separate the blues from the reds. We are able to classify correctly using this unit circle. How about this case? All 3 reds and all 3 blues. Yes, we are able to do the classification correctly. In the last case, all 3 are blues, so the circle doesn't have to enclose anything. So these 3 points can be shattered by a circle. Yes. Now, let's look at 4 points. Can 4 points be shattered by the same unit circle? Answer is no. You cannot shatter these 4 points. Can you enclose the 2 red dots? No, you cannot. So the VC dimension of H is 3. Now a note on the sign. So this is an expression for a unit circle, and you see that less than r squared. So it defines the interior region, and maybe that's the region that should be the negative category. Anything belonging to a red class, let's assume, should be what the inside the region defined. And so, yes, the red here is remaining inside this region. Otherwise, if we define a circle like this with this greater sign, then the region it defines is outside the circle, and so the red has to be outside the circle. Now we have to place the blues inside the circle. And otherwise, if we just say a unit circle, either inside or outside, either way works, then both situations, either this or this, then we can say both these situations are equally good. They're both doing the classification correctly. How about an ellipse? So let's look at an ellipse in 2 dimensions. Can 4 points be shattered? Yes, 4 points can be shattered, and one can easily verify that all possible labelings of 4 points, if you place them strategically, in such a manner that all 4 points can be separated, then these 4 points are shattered by the ellipse, and so the VC dimension of the hypothesis space of ellipses is 4. Now, can these 4 points be shattered by an ellipse? The answer is no. We obviously cannot shatter these 4 points by an ellipse because they're all in a straight line, and there's no way we can have an ellipse enclose these reds. However, as long as the ellipse is able to shatter any placement of 4 points, we are free to choose the placement. As long as it's able to shatter any placement of these 4 points, then the hypothesis space has a VC dimension of 4. It doesn't have to. In order to have a VC dimension of 4, the hypothesis doesn't have to be able to shatter any placement of 4 points. As long as only one properly placed set of 4 points can be shattered by a hypothesis, then the VC dimension of the hypothesis space is 4. So some set of 4 points must be shattered. VC dimensionality of lines and hyperplanes. A set of lines in 2 dimensions, the VC dimension is 3. So if you have 3 points in a plane, all possible labelings of the 3 points can be classified properly by a straight line. Now we are assuming that this straight line is flexible enough to place on its left the red points or on the right the red points. It doesn't matter. One side or the other, it doesn't matter. So all labelings of these 3 points can be shattered by straight line, and so the VC dimension of the set of lines in 2 dimensions is 3. The VC dimension of a set of planes in 3 dimensions is actually, you can reason, it's 4. And the set of hyperplanes in n dimensions, the VC dimension is n plus 1. This is a generalization of the line and the planes. So in 2 dimensions, the VC dimension is 3. In 3 dimensions, the VC dimension is 4. In n dimensions, the VC dimension is n plus 1. Now, is it true that some sets of hypotheses can have infinite VC dimensionality? The answer is yes. The set of all convex polygons can shatter infinite points in a plane. You have to place the points strategically, any number of points, and a convex polygon will be able to shatter it. A set of sinusoids can shatter infinite points in a straight line. So the VC dimension of the set of sinusoids of all frequencies is infinite, as this figure shows. So let's look at path bound once again. So with probability greater than or equal to 1 minus delta, this is the upper bound of the true risk. And VC dimensionality, here we want to keep this term as low as possible, and this VC dimension is, this factor is more important than this one because it's inside the log, and it serves to increase the second term when the VC dimensionality is increased. Therefore, we should keep the VC dimensionality as small as possible, and because it reflects the complexity of the model, and we also know from the bias variance dilemma that the The more the complex is, the more the variance of the model. It becomes more sensitive to small quirks, or oddities in the finite set of samples in the model. And the VC dimension is to be kept as low as possible. Now let's look at the pack bound specifically for support vector machines. So this is an expression for the support vector machine pack bound. VCH is, well, the first expression is, this is the same as before, but the VCH of a support vector machine is equal to R square W transpose W. And R square here is max of the L2 norm of squared of a sample. So it's not part of the support vector machine. It's the sample space that the support vector machine is dealing with. That's R square. And what about W transpose W? Now, during SVM training, we specifically try to lower W transpose W. And this is a very good reason why we want to lower W transpose W, because then the VC dimension is also getting lowered. Now, this expression doesn't take into account directly the margin of separation. If we look at the margin of separation, we have another similar expression, and that's this. E true H, that's the true error, is less than equal to E train gamma of H plus some constant C times this expression here, and the denominator here, this gamma, is the margin of separation. So if the margin of separation is high, then this quantity becomes low. Consequently, the second term becomes low. And the true error gets closer to the training error. Gamma is the margin of separation. And E train gamma is the fraction of samples inside the margin, because we need to take into account what's inside the margin, correctly classified and incorrectly classified, and what's not inside the margin. So we have to define our E train, the training error, as anything that lies inside the margin or crosses the margin to the other side. Those are the training errors. And so we can see that the VC dimensionality of a hyperplane gets lower if the margin of separation is made high. And that's the reason support vector machines are preferred in classification and regression. And this approach is called structural risk minimization. End.